Okay, today we're going to talk about the chain rule. We've looked at the chain rule as it applies to like the basic Calc 1 type of chain rule. But there are additional chain rules when we're dealing with multivariable functions. In particular, if we have a function that is parameterized. Okay, so there's two different ways to parameterize a function. The first way is on a single variable. So let's say we have z is a function of x and y is differentiable. Differentiable, I think that's right. All right, is a differentiable function in x and y. Okay, but all right, so where we're parameterizing on t. So let's say x equals g of t and y equals h of t. All right, so f of xy is a differentiable function of x and y, where x and y are parameterized on t. All right, then it turns out that f is a differentiable, I'm going to abbreviate that, differentiable function of t, which means I should be able to find dz dt. All right, so to find dz dt, just regular d, right, because now we're talking about a single variable here, dz dt, regular d's. All right, we have a chain rule form that says we do the partial of f with respect to x times dx dt plus the partial of f with respect to y times dy dt. Okay. All right, now, because we're mixing partials and regular derivatives, and because we're mixing x and y and t, this is not something you normally use to just find like a function derivative. You're usually looking for it at a point. All right, so when we do these problems, you'll see in the book when you look at the homework, when we do these problems, we're looking for the partial at a specific point. So as an example, let's say I have z equals x squared y plus 3 xy to the fourth. And we have the parameterization for this, x equals sine of 2t, and y equals cosine of t. And we are interested in this derivative when t is 0. All right, so because I know I can hear some of you asking the question, yes, all of this will be given, all right? There's always times when you have to find a parameterization, but if you're just asked to find a derivative this way, you'll be given the parameterization. Okay, so in order to find dz dt, right, so this is what we want to do here, right? Find dz dt. Okay, so I need all of this. So my advice, calculate everything separately. All right, so let's do the easy ones first. Dx dt and dy dt. Okay, so dx dt is going to be 2 cosine 2t. dy dt is going to be negative sine of t. All right, and all right, hang on. This is one thing at a time. All right, and then we need the partials, right? So we need the partial of z with respect to x. So this is good practice here. Remember, when we're doing the partial of z with respect to x, y is a constant. So over here, I'm taking the derivative of x. So that's going to be 2x y, because y is a constant. Plus, again, over here, the derivative with respect to x is going to be 3. Derivative of x is 1, so y to the 4th. And then we need partial of z with respect to y. All right. So again, back up here now, y is the variable, x is the constant. So this first term here, the derivative of y is 1, so that's going to be x squared. Over here, with respect to y, so that's going to be 4y to the 3rd, so that's going to be 12xy to the 3rd. All right, now, because I want all of this at t equals 0, all right, I need to figure out x and y, and then all of this. All right, so at t equals 0, x is going to be sine 2 times 0, which is 0. Y is going to be cosine of 0, which is 1. All right, so now I can plug everything in. All right, so let's see, how do we want to do this? I think I want more board. That's good enough. Okay. All right, so I need dx dt, right? So dx dt at t equals 0 is going to be 2 cosine 0, which is going to be 2, dy dt at t equals 0 is going to be minus sine of 0, which is 0. The partial of z with respect to x at, let's see, x is 0 and y is 1, so I'll write it that way. Right. Is going to be, let's see, x is 0, y is 1. So 2 times 0, so that's 0. Y is 1, so that's 3. And the partial of z with respect to y, again, at 0, 1. All right, so x is 0, so that's 0. Again, x is 0, so that's 0, so that's equal to 0. All right, and then I just want to put this together with the formula. All right, so dz dt at t equals 0 is going to be the partial of x, I'm sorry, the partial of z with respect to x, which is 3, times dx dt, which is 2, plus the partial of y with respect to, I'm sorry, the partial of z with respect to y. I don't know why I keep wanting to say that upside down. Times dy dt, which is also 0. All right, that makes that easy. So that whole thing is going to be 6. Okay. Now keep in mind, if you didn't have, right, if you didn't have that value, this would just be a mess of functions, right? This would just be everything up here put together, right? The partial of z with respect to x times this, plus the partial of z with respect to y times this. You know, there's a lot of t's and x's and y's involved. You could sub in the actual parameters to have everything in terms of t. It just gets really messy. So anytime you're doing this, you're doing it at a specific point. All right. So this is what we're going to do if we have a parameterization in a single variable. Right? If we have a parameterization in multiple variables. All right, for us, 2 variables is probably enough. All right, this is the second case of the chain rule. All right, so again, we have z equals f of x, y is differentiable in x and y. And this time the parameterization is going to be parameterized by a different 2-variable function. All right, where x is, we'll say g of s and t, and y is h of s, t. All right. So both of these are differentiable in s and t. All right, then just like before, all right, we have that f is differentiable in s and t. All right, that same thing holds. All right, then what we can do here, because we still have 2 variables, is we end up with 2 partial derivatives, one for s, one for t. So I can find dz dz, ds. All right, so what we're going to do here is do the partial of z with respect to x times the partial of x with respect to s plus the partial of z with respect to y times the partial of y with respect to s. All right, and then dz dt is going to be the partial of z with respect to x times the partial of x with respect to t. Am I doing that right? Yes, I'm doing that right. Good. Plus partial of z with respect to y times the partial of y with respect to t. All right. Now you may ask, why would I want to do this? The idea here is actually doing the parameterization, like replacing x and y with g of st and h of st, is complicated. All right. Usually way more complicated than you're going to want to deal with. Okay. I'm not going to go through an example with this because it really is just a matter of calculating each of those, but I want to show you something here. The first case that we have for the chain rule, right? If I go back up here, right, our first chain rule function up here gives us a more complete description of implicit differentiation. So y'all remember implicit differentiation from Calc 1, right? In Calc 1, you had essentially a formula that involved x and y, where you assume y is an implicit function of x, right? But it's one that you can't solve for. So, for example, right, a circle, right? The equation of a circle, let's say x squared plus y squared equals 4. I don't know, something like that. All right, you can find the rate of change or find the slope of the tangent line anywhere on that circle without having to solve for y. You can't solve for y implicitly. If you try to solve for y, you're going to end up with a plus or minus, which means you're either dealing with the top half of the circle or the bottom half of the circle. All right, not the whole circle at once. And you would go through and you would use implicit differentiation on this, assuming that y is a function of x. And you would pick up those dy dx's, and those dy dx's at the end you would have to group up and solve for, and the algebra got kind of messy, and you know there was all this stuff that went on. In Calc 1, this can be a difficult concept. It can be tricky to solve, and the algebra can just get really awful. All right. If we use this concept here that a function like this, all right, can be written as a function of two variables by doing something like subtracting the 4 from both sides. So I have x squared plus y squared minus 4 equals 0. And then defining my function, let's call it capital F, of xy to be x squared plus y squared minus 4. All right, then looking at that, we're only interested in where that is 0. All right, so what we're going to do is we're going to define, so let me just, I'm done with that as my example there. All right, we're going to define a new function, capital F, of xy, where y is a function of x. All right, so we're going to look at f of x equals 0. Okay. All right, now this is going to be defined for all x in the domain of f, the domain of lowercase f. All right, then when I differentiate both sides of this, okay, when I differentiate both sides of this, I get the partial of f with respect to x times dx plus the partial of f with respect to y dy dx equals the derivative of 0, which is 0. All right. So I can now take this equation here, which is my formula equation, and I can solve it for dy dx, right? This is just 1. So this becomes the partial of f with respect to x plus the partial of f with respect to y dy dx equals 0. All right, so that means that dy dx is going to equal, let's see, if I bring that over, I'm going to have the negative partial of f with respect to x over the partial of f with respect to y. All right, so basically your implicit differentiation simply becomes negative fx over fy. All right, a lot simpler than trying to go through the Calc 1 method for doing implicit differentiation. All right, let me move this down and we'll look at a quick example here. Okay, all right, so let me come all the way down here. All right, so we just said dy dx, right, dy dx is negative fx, yeah, negative fx over fy. All right, so if I have the function, or I have the equation rather, x to the third plus y to the third equals 6xy. All right, so there is your equation that you want to find dy dx for, right? So find dy dx. So if this was a Calc 1 class, right, you would differentiate this side with respect to x, this side with respect to x. You would have to collect up your dy dx's, solve for dy dx, right? So if I use my Calc 3 method here, the first thing I have to do is have this set equal to 0, so I bring that over. So I've got x to the third plus y to the third minus 6xy equals 0. All right, fx, right, the derivative with respect to x is going to be 3x squared minus 6y. Fy is going to be 3y squared minus 6x. Right, so dx dy dx is going to be negative fx, 3x squared minus 6y over 3y squared minus 6x. And I'm done. Okay. Don't hate too much on your Calc 1 professors, all right? They couldn't teach you this at the time. But that is a lot easier. All right, so, I mean, when you go back and you look at problems now where you have to do this kind of implicit differentiation, you now have a new tool. You have a new tool that you didn't have in Calc 1, which is partial derivatives. Okay. Now, if you have something more than two variables, right? If you have a function of an implicit function in R3, all right, so this was an implicit function in R2. All right, if you have an implicit function in R3, you simply end up with two of these, right? You're going to do the partial of z with respect to x and the partial of z with respect to y. So, let me, well, actually, I've got room on the side here. Let me do it over here. I'll just wall that off. All right, so this here is implicit in R2. So, implicit in R3, all right, becomes partial derivatives. So, instead of dy dx, you're going to have dz, partial of z, with respect to x, which is going to be fx over fz, and the partial of z with respect to y, which is going to be fy over fz. Okay, so this is basically it for the chain rule or implicit differentiation, which is really what we're doing here in R3.